let's get started. So welcome everyone. So this is M4 Dynamics. I'm Professor Derek Moulton. Okay, we'll have 8 problem sheets in the course. There's the basics there. We'll talk a little bit about what are we doing in this course. So it's a very rough objective. What we want is to develop a mathematical framework for motion. Okay? I should say, sometimes my writing starts to shrink as the lecture goes on, so if it shrinks to the point where people in the back find it hard to see, just shout and do that or something. Hopefully that's large enough. Mathematical framework for motion. So what do I mean by that? Roughly what I mean is we're going to take Newton's laws, and we'll sort of take those as our ground truth. We'll maybe discuss the situations where it's not actually ground truth, but mathematically we take Newton as ground truth. Plus the geometry framework you developed last term, plus some vector calculus, maybe some differential equations to describe motion. Okay? Let's just say that. So, to give you a simple example, so I want to describe that motion. Okay? What does that even mean? Okay? I mean is, tell me what the forces are that we have in that simple experiment, plus the initial conditions, which is more or less what I did, giving a little of the toss. And I want to have a mathematical description of the motion. And you realize that this is more complicated than maybe it appears, because it's spinning, right? So that's what we want. At the beginning of the course, we're going to kind of ignore that, and we'll imagine that the pen is a smushed up point mass. But by the end of the course, we want to be able to describe that rotation as well. And the rotation means we need to think about the geometry, and then we need to, what are the balance? How does Newton inform us about not only the motion of, say, the center of mass, but the rotation as well? Okay. And then the question is, how many variables describing that motion, how many variables do I actually need? Okay. That's a question for us to think about. So set Newton's laws, we'll sort of take that as our ground truth. Those that have done some physics or even just followed, say, popular science will be well aware that Newton's laws are not the ground truth of the universe as we know it, right? General relativity, quantum mechanics, these have sort of supplanted the truth that Newton had discovered. Nevertheless, Newton's laws do a fantastic job of describing everyday experience like that experiment. And in fact, if you tried to describe that experiment using something like quantum mechanics, it's going to be much, much harder, and you're not going to get a different answer in the end than Newton would give you. And to that point, what do I hope people take out of the course? There's maybe kind of 2 different kinds of people in the room. So there are those of you that are a bit put off by applied maths. It's okay, I understand. You say, I like the purity of mathematics. I'm only here because I have to take dynamics in my first year, and then I can go do some proper mathematics. If that's you, I'm not mad. I hope that you will nevertheless appreciate that what we're going to do is reasonably rigorous. In other words, we're not going to be stating and proving theorems, but we will be developing these things in a more or less rigorous way. We say, I take Newton, that's more or less my axioms. We use some geometry, and we develop very clearly to the point where we can describe the motion of that flying pen. Okay? Others of you that are a bit more inclined towards applied mathematics or somewhere in the middle, this material forms a fantastic starting point for lots of other things. And Newton's laws, Newtonian mechanics, as it's called, is still, as I said, incredibly useful and incredibly relevant. It's a stepping stone to understand these further developments like quantum and general relativity, which we have on offer in second, third, fourth year here. I don't think you can really understand those theories very well if you don't start with these. But even on following Newton, where we sort of take Newton as truth, but allow more complex phenomena of developments over the past few hundred years, fluid mechanics, solid mechanics, elasticity, physiology, there are lots of topics that are very relevant current research topics that really take Newton's laws as their starting point and develop things in a very rigorous, principled way. Okay? Right. Yeah, so that's my spiel about what we might try to accomplish in this course. Let's get into some details. So the first well, I said we're starting with Newton. We need to say what Newton was actually thinking about, right? So this is Chapter 1 in the lecture notes, and our starting point here, Newtonian mechanics. So, and maybe it's a bit more about what do we mean by the word dynamics. We mean the motion of an object or objects through space and time, or in space through time. So, objects moving through space over a period of time. Let's look at each of those words individually. So, space for us, that just means Euclidean R3. And I want to describe the position of an object in that space. This is familiar stuff. We need a reference frame, we need an origin, and we need a coordinate system, and we need a position vector, right? So to describe position, it's a reference frame, which we're going to call S, and that just means an origin and a coordinate system. So I have an origin and I have a right-handed, I mean, we don't have to, but let's use the convention of using a right-handed orthogonal coordinate system, right? So three axes, which we might call the x, y, z. And that's the origin O. So that by S, I mean all of that. I mean, where is the origin and what is the orientation of my coordinate system, okay? By an object, I've already touched on this. The object is the pen, but what is the pen? The pen is made up of molecules. The molecules are made of atoms. The atoms are made so and so on. Right? What is the object? The object could be the pen as a single entity. It could be more than that. Right? We have to make a choice. So I said at the start, by an object, we'll think of a point particle, a point mass. And this is very much an idealized construct. It's an idealized object. In particular, maybe the biggest difference, a point mass you would think of like a small little ball, except it's different from a ball because if I do that experiment with a tennis ball, the tennis ball still rotates and I can try to describe that rotation because the ball has an orientation. A point mass has no orientation, so rotations are completely irrelevant to point masses, which is why it's a nice, simple place to start. So it's an idealized object. Let's locate it at position r of t. So r is the position vector from our origin, and explicitly noting that that's going to be a function of time, right? So here's our point mass, and that vector is r. And what do we mean? We also have time. And the key point when we talk about time is that it's the sort of simplest, intuitive construct of time, which is that it's the same for all observers, what we call absolute time. And indeed, everyone measures the same intervals of time, right? Same intervals of both time and distance. So if you and I both start our stopwatches at the same time and stop them at some point later, we'll always agree. And we'll always agree if we make measurements as well. This is sort of what Einstein realized wasn't correct. There is no absolute space and time. It depends on relative motion. But for Newton, this is what we take. Okay? And that means that if I have two different coordinate systems or two different frames, so let S and S prime be reference frames, and vector r and vector r prime be the position vectors of the same point mass, so here's the picture. That's frame S. Here's position. Here's our point mass, vector r. And over here we have a different origin, a different orientation of the coordinate system, and I measure the same point from there, call that r prime. What must be the relationship between these? This is right-handed orthogonal. This is right-handed orthogonal. It must be just a rotation and a translation that takes me from there to there, right? And what that means is that whatever position vector you get here, the same position vector there is just a rotation and a translation away. Okay? So we can say that S prime differs from S, and this is what you did last term in geometry, right? Differs from S by a translation and or rotation. Thus, my position vector r prime is some let's not worry about working out more than that. Some orthogonal matrix R, and X is a translation, and that translation could be a translation in time, but that's the statement that they're related by a rotation and translation. So RTR is identity. Okay, technically there could be a reflection, but when we're thinking about physical frames, reflections are not super useful. Reflections change right-handed systems to left-handed systems, and we don't really want to do that. So really, I measure the pen from here, you measure the pen from over there. What's the difference is you're over there and your system is rotated related to mine. So that R would have determinant equal 1 for most of us. If you guys remember from last term, determinant 1 for rotation, determinant minus 1 for reflection. Okay. Let's then go to Newton. Come over here. So what are Newton's laws? Well, first, let's just situate ourselves a little bit better. Let that vector r of t have coordinates x, y, z. Each functions of time. Let that be our point particle. I think these pens would be working better on day 1, but it's technically day Michaelmas +1. So let's define some things that I think everyone's well aware of. The velocity vector we'll call v is just the time derivative of r. Which we will use the over dot for time derivative. And the over dot just carries through to each of those. So that's x dot. That's the vector x dot, y dot, z dot. Speed is the magnitude of velocity, which is the square root hopefully you've already gotten good habits from last term, but I'll just remind you, try not to be lazy about doing something to signify in your own writing what's a vector and what's a scalar. Right? So I will always use the little curly under thing. The typed notes, I think, are probably using boldface for vector. Velocity is a vector. Position is a vector. Speed is a magnitude. Speed's a scalar. Right? And acceleration, one more derivative. V dot dot, or that's of course V dot, which is R dot dot, second derivative time. Okay, so before I start writing down Newton's observations, let's give ourselves a simple example. Suppose a particle has constant acceleration q and starts at the origin with initial velocity u. Find the trajectory. Okay. Maybe worth saying at this point, people who did their A levels here probably did this, what do you call it, SUVAT? SUVAT? I want you to almost forget that. I know this is very useful. There's a very nice formula. If we sort of take SUVAT as a given, then we're not really being very axiomatic, right? So we don't need any of that. We're going to say, I have these relations, and everything we do. I know your tutors will be a bit annoyed with you if you're solving problem sheets by doing a SUVAT thing. So I'm giving you that heads up now. We're going to, and some people that didn't do A levels here are like, what the heck is he talking about? SUVAT is this like formulaic way of getting positions, and I don't know. It's basically you start from velocities, accelerations, and you're more or less integrating these equations. And it's a nice shortcut way of doing that, but we're not taking shortcuts here. So we don't have any SUVAT. Find trajectory. I have an acceleration. That means I know r dot dot is a constant, and I just need to integrate twice. Okay. R dot dot is q. Find trajectory means what I want to know the function r of t, and that's what that wording means. R dot dot is q. Q is constant, we've been told, so I integrate that once. R dot is qt plus a constant vector, and this second line we start at the origin. That means that r of 0 at time 0 is 0 at the origin, and the velocity r dot of 0 is this vector u. So if I stick in t equals 0 here, we get right away that that c must be u. And then I can integrate once more, and I get r of t is 1/2 qt squared plus ut plus another constant, c1 if you want, but that one is going to knock that one out. Okay. Fine. So we have a description of position, velocity, acceleration, but really Newton was thinking about forces, and to connect positions and accelerations to forces you need momentum, and this is where mass needs to come in. So momentum, in fact there are two different kinds of momentum. There's linear momentum, and then later in the course angular momentum, which would be sort of momentum of rotating, but starting with the easier one, linear momentum is a vector p, which is m times v, mass. M is the mass there. So m greater than 0 is the particle's put that. It's the particle's mass, and I'm going to make a distinction here. I'm going to call that the inertial mass, and we'll make a little bit more sense of why putting the word inertial there a bit later. So that's a mass measured in kilograms, for instance. And now you get a little more sense. A point particle is very much idealized. It has a position and it has a mass, and that's all it has. Okay? So now we come to Newton. Newton had 3 laws, as probably seen, and Newton's first law says that in an inertial frame, don't come to that wording in a moment, an inertial, let me just clarify, I mean an inertial reference frame, using the word reference over there. But particle moves with constant momentum. I'll abbreviate momentum that way. Unless acted on by an external force. Right. A couple of things here. So constant momentum, momentum not changing in time. Now there are two ways for momentum to change in time because it's mass times velocity. The mass could change. If the mass of our point particle changes, the momentum has changed. For the most part, we won't ever think about the mass changing, though there's thought experiments where you could have mass changing. So P constant means P dot equals 0. If M dot equals 0, constant mass, then of course we conclude that V dot is 0. But V dot is A, so that means there's no acceleration. So what Newton says is that if you don't do something to the particle externally, then, and its mass isn't changing, then its velocity isn't changing. It's going to move in a straight line. Okay? But this is only true in an inertial reference frame. So what's an inertial reference frame? Sometimes you look up inertial reference frame and the logic gets circular. Say inertial reference frame is a frame in which Newton's first law holds. But Newton's first law only holds in easiest way to think of an inertial reference frame is a non-accelerating frame. So here's a thought experiment. Standing on ice, okay? And if nothing happens. If I'm standing still on ice, I just keep standing still. Okay? If I'm sliding on the ice with some velocity, and I'm talking about ice because it's more or less frictionless. If I slide on the ice with a constant velocity, going that way, I keep going that way unless something else happens to me. Of course, I don't slide that way forever because there are external forces. What external forces are there on actual ice? There's a little bit of friction, but what else is there? There's air resistance, right? I'm sliding this way. I'm going through the air is pushing on me. There is an external force. If I did that in a vacuum with no air, I would just keep going that way unless something external happened. Okay? However, let's think about an alternative version of that experiment. Put this ice rink on a train. That'd be a fun idea. Ice rink on a train. And now let's suppose the train, two scenarios. The one is that the train is going in a straight line at a constant velocity. Okay? The train is going at a constant velocity, and you do that same experiment, give someone a little nudge on the ice, and maybe it's a vacuum. It's a tough one to set up. We have a vacuum in an ice rink on a train going at a straight line with a constant velocity. I think we can make that work. What happens? Nothing different, right? That person slides at exactly the same velocity in the same direction. Nothing changes. Okay? There's no external forces. That's an inertial frame. And what I mean by the frame is somewhere in that ice rink we put an origin, right? We give ourselves an S, and we measure that person's position from that S. That would be an inertial frame. Compare that. Now suppose the train goes around a curve. You probably have this sense. What happens differently if the train goes around a curve? I'm sliding on the ice, having a nice time. Train goes around the curve. Okay, suddenly I'm being pulled this way. Why am I being pulled this way? There are no external forces. It's the exact same setup. I look around me. There are no external forces. There's no air, and yet my momentum changes. Or the train starts accelerating. It keeps going in a straight line, but it starts accelerating or decelerating. The train slams on the brakes. Suddenly, I go forward much faster, right? So non-inertial frame, if the train is accelerating either by changing its velocity in a linear way or going around a curve, that's non-inertial. And the particles, so basically this statement doesn't hold, because in that non-inertial frame, there are no external forces, and yet the momentum changed. Okay? Those forces, they're called fictitious forces, and we experience them all the time because we ride on trains and we feel ourselves being pulled to the outside, thrown to the outside, or in a car going around a curve. And we're going to come to those in week 7 or 8 and have the mathematical description of those. But for now, we'll mostly be sticking to nice inertial frames that are non-accelerating. So non-inertial frame so, and then we'll just add some words. So compare a train moving with constant velocity versus accelerating train. In particular, the accelerating train creates these so-called fictitious forces, which we'll come to in chapter, I don't know, something later in the course. Okay. At this point, you might say, okay, but even in the train's going straight, the train is on the Earth. The Earth isn't going straight. The Earth is spinning. It's going around the sun. Effectively, it's very hard to get a proper, truly proper inertial frame, but it becomes the scale of things. In that experiment, the acceleration of the Earth is completely negligible in affecting the experiment. And so that is as good of an approximation to an inertial frame as we can find. Okay. So that's Newton's first law. Let's come to Newton's second law. This is the one we probably think of more often. In an inertial frame, the dynamics which I mean the motion of an object, satisfy this sort of F equals ma. We know this equation. F, I'm going to write it this way, F is d dt of p. This is really what Newton's law says. F is going to be the external forces. P is our momentum. The time rate of change of the linear momentum is the sum of the forces. But that's equal to ma if m is constant. Or mr dot dot, that's if m constant. What would happen if you just want to think of a quick thought experiment of m not being constant? I'm on my ice skates on a train somehow. I'm going nicely in one direction, and while I'm going in that direction, I shed my backpack. Right? What happens to me? I go faster. I've brought down m. There's no external forces on me, so p should stay the same, so v is going to go up. Okay? So there's a sort of physical scenario where m might reasonably change, but for the most part, we'll think of m as being constant. And if m is constant, this is our very famous Newton's second equation, and in terms of r, mr dot dot. And I've said it, but let's write it. F here is the total external force applied to the object. Right? We'll say more about how we get those forces. So note, and particularly people who have done some mechanics and physics in A levels, I think it's really important to like be clear to yourself that that's a vector equation. Right? And the other note is just to be clear that we've stated this, that I'm in an inertial frame. Okay? Sometimes you say the definition of an inertial frame is a frame in which Newton's second law holds. It's another way of defining it. So I do an experiment. I'm on this train. I'm on this ice rink. I don't know if the train is going around a bend or not. Say I'm trying to work it out. I'm in the dark, and I can't look out the window. One thing I can do is I can do an experiment, and I can sort of see if that equation holds. I say, throw a pen on the ice or in the train. And if Newton's second law holds, if the acceleration of that particle matches the forces of gravity, which I know about, then I'm in an inertial frame. And if it doesn't, then there's these extra fictitious forces, which means it's coming from a non-inertial frame. For this is really just repeating what I wrote above, but worth repeating. For a non-inertial frame, Newton's second law doesn't hold unless you add the contributions of the acceleration of the frame. I called them fictitious. Let's call them extra this time. Extra forces. And this is the subject of the end of the course, which I now see in my notes says chapter 8. Okay. Leave those where we can see them. So Newton 1, Newton 2, F equals ma. Newton 3, come back over here, says if I have two particles, and particle 1 exerts a force, I'm going to call it F(1). That's the force on particle 2 from particle 1. So that particle 1 exerts that force to particle 2. This is not the way Newton phrased it, but that's the way we're going to phrase it. Then particle 2 exerts an equal and opposite force. So that's F(1,2), which is minus F(2,1) on particle 1. Right, so that's sometimes stated as every action has an equal and opposite reaction, but that's sometimes a bit hard to get some intuition for. In fact, there's often kind of a misconception about this law of Newton. So, for instance, here I am standing on Earth, and let's say in this sort of inertial, pretty close to an inertial frame, I'm not accelerating. The Earth is applying a force to me, right? Clearly. Gravity is pulling me down, and yet I'm not accelerating. So Newton's second law says that since A is 0, F must be 0. And there's this F down of the Earth, so there must be a force going the opposite direction. There is. The floor, I'm pushing on the floor is pushing back on me. That's called a reaction force. Okay? That's going to be really important in our development. That is not Newton's third law. That reaction force is there, and it must be there because I'm not moving. Okay? Newton's third law is a bit different. Newton's third law says, the Earth is applying a force to me, F21. I'm particle 2. I must be applying minus F21 back to the Earth. That's it. I'm pulling on the Earth up. I have gravity. Not loads. I have some. The Earth is pulling me down. I'm pulling the Earth up. Newton's third law says those forces are equal and opposite. Perhaps you're thinking, that's crazy. The gravitational force of the Earth is massive, and you, tiny little you, your force is surely exactly the same. My gravitational force pulling the Earth towards me is exactly the Earth's gravitational force pulling me down. Okay? We'll come to that, a formulaic expression of that gravitational force later. And just to kind of, if that's blowing your mind, what's the difference in Newton's second law? So if I do Newton's second law applied to the Earth, the Earth has a big M. Right? So even though the Earth feels my gravitational force towards me, the Earth's M is much bigger than my little m for my MA being pulled down by the Earth. Okay? But Newton's third law is the equivalence of those two reciprocal forces. For us, the biggest thing Newton's third law will do is let us take a really complicated object like a pen, which is made up of who knows how many atoms, and each of those atoms made up of whatever, and take all that complexity and say that actually all those molecules are pulling on each other and pushing on each other in a reciprocal way. So if we do the mathematics correctly, none of them matters. It's a question of degrees of freedom. How many degrees of freedom do I need to describe that experiment where I tossed the pen? You might say, oh, you need one variable per atom in the pen or per molecule in the pen or something like that. No. As long as the pen sort of remains rigidly fixed, each of those forces, internal forces, basically then will show later in the they all cancel each other out, and we can describe the pen with 3 degrees of freedom for its position and 3 for its rotation. Okay? We'll come to that. Okay, so that's Newton. And how much time have we got? Maybe just enough to start the next bit. Any questions on these 3 laws? Okay, so it's a slight change in tone, but what I want to start now is what's called dimensional analysis. And we start from a very simple statement. Physical quantities have dimensions. The purists out there, you're welcome to groan at this point. We're mathematicians. We don't like to think about units and dimensions. We just like numbers and functions. Nevertheless, if we're thinking about using our mathematics to think about physical things, this is not only true, but actually really useful for guiding our mathematics, because we can argue about how things must combine in order to make sense in terms of their dimension. So what we do is we observe, or we can break things down into fundamental dimensions, which consists of lengths, let's use L, time, capital T when I'm thinking about the dimensions of time. Mass is capital M for that. And if we're doing something with electromagnetism, which we'll do just a little bit of, we have charge Q. So, just to set, when we are thinking about the dimensions of something, the notation that's normal is to use these little square brackets. So square brackets of I put something in the middle means dimensions of the thing in the middle. So for example, we've been talking about forces. Force itself is not a fundamental dimension. Let's suppose you never heard of forces before, just based on what we've done so far in the past 40 minutes or so. And I've told you that those are the fundamental dimensions, length, mass, and time. How can you tell me what is the fundamental dimension of force? Do we have enough information? No.
It's just the dimension of the
Yeah, Newton's second law tells us that force is balanced by mass times the second time derivative of position, and position is a length. So this is the same as the dimension of m, and I'll write it this way now, d squared r dt squared. That's a mass, that's a length, that's a time squared. So ml t to the minus 2 is the normal way to write that. That's the dimension of force. If we work in SI units, then we're thinking about kilograms, meters, and seconds. Mass, length, time. So I should maybe, m means meter, just because we've had m appear a few places. S is seconds, and I think kg, kilograms. So we will also use, because that combination is quite important, there's a definition of a unit, which is the Newton, and the Newton is defined as 1 kilogram meter per second squared. So that's a unit, sort of a fundamental unit of force, if you want. Okay. So let's make one more kind of comment on a bit of the value of dimensions. Which is the statement that I can only combine quantities if they have the same dimension. Right? It's a very fundamental idea, and yet sometimes when we're just doing algebra, doing mathematics, if we're not thinking very clearly about dimension, we might forget that fundamental notion that I can only add quantities of the same dimension. I'd say in a way, when you're doing a problem, this is a nice thing to have in the back of your head. It's a way to check whether perhaps you've made a mistake. Right? If I have given x plus t somewhere you're trying to have in your equation, and x is a length and t is time, that's quite clear that something went wrong. I shouldn't be adding length to times. But a place where it's maybe a little bit less obvious is when you think about like the arguments of exponentials or trig functions. Right? So exponents and arguments trig functions that's my abbreviation for functions. Trig functions must be dimensionless. And there's a quick way to think about that, which is the Taylor series. So observe. We'll stop after that. If I write the expression e to the x, and you say, what's x? Oh, it's a length. Okay, wait, so that has units of length, but e to the x is the same as 1 plus x squared, dot, dot, dot. So if x is a length, then somehow this expression is the same as something that has no dimension plus something that's a length plus something that's a length squared. That makes no sense, right? So sometimes we'll have expressions like that, but there's a sort of hidden 1 over length living in that exponent as well. The whole of that quantity must be dimensionless, or that expression makes no sense, right? So I lead the units of x must be 1 is the statement that has no dimension. So if x is a length, then there's a sort of hidden 1 over length in there. Okay. Right, we'll pick up with that on Thursday. Let's stop there. And each time, as you probably know, it'd be great to have some help with the boards. Otherwise, see you Thursday. Let's get going. So we were talking last time at the end about dimensional analysis, thinking about the actual units and the way units, quantities of different units must combine. Noted that on the one hand, that's a way for us to make sure we're not doing something sort of silly, like having meters inside of a sine function, something like that. But actually, there's more powerful than that. Done in the right way, you can really infer quite a lot about the behavior of a system just from thinking about how the units might combine. So here's a simple example. I drop an object from a height h. And I ask the simple question, when is it going to hit the ground? Okay, so there's just falling under simple gravity, okay? Well, you could do this in school, right? The sort of straightforward way, or the direct calculation, the standard calculation. Would be, I define, say that as the z-axis, and Newton's second law projected onto that axis would say that the mass times the height, second derivative of the height, that's the acceleration, is equal to gravity minus mg. And I have z of 0 equals h. And I've just let it go, so I had no initial velocity. Z dot of 0 is 0. You've probably done this sort of exercise before. You can just integrate that, apply those initial conditions, and you get Z is h minus 1/2 gt squared. And of course, the object hits the ground when Z goes to 0, which gives a landing time of t land of root 2h over g, right? Okay, don't think there's anything tricky there. Here's an alternative way of getting not quite that exact answer, but an almost equally useful one. There's an alternative, which is to think about the physical quantities in the system. Let me switch to blue. Okay, so I've got, and in particular, what are their units, right? So I've got gravity, G, and we've used this little square bracket to say that the units of G. Gravity is an acceleration. Acceleration is a length over time squared, right? So that's L. We use L for length, T for time, L over T squared. I've got the initial height. And of course, the units of that is the length. And I've got time, right? And then what I do is I say, so this is what I kind of want to know about. I want to know about the time this object falls. And I say, well, what to do is I want to seek a relationship where t is some function of g and h, which is the statement that those are the sort of things in the system, and that one should depend on the other two, right? You might be tempted to say, oh, well, there's mass as well. The object has some mass. You would see quite quickly that that's not going to work if I put a mass in there, because mass is its own separate unit. And we'll see in a minute sort of, I mean, you can understand from up there why mass doesn't matter, because the mass is appearing on the left and the right side of the equation. But in terms of units, if I tried to say that time is a function of g, h, and m, that m is stuck, right? There's nothing to balance the m. Whereas the g involves length and times, and h is a length. Okay. So if I wanted to do that, in fact, you can kind of just work it out, almost spot it just looking at it. But if I want to do that formally, what is that relationship? What I can do is say, let's suppose that t is h to some power a and g to some power b. And I don't know what a and b are. Now I'm going to put in the units of these things. Let's say for some a and b. Okay, put in the units, so that reads that t, capital T, is unit of the left-hand side, h is a length, so I get L to the a, and g is a length t to the minus 2, so that's lt to the minus 2 to the b. Now I expand, so that's L to the a plus b, and I have a t to the minus 2b. And now it creates a linear algebra system, because that combination on the right has to end up being just a length for this to make sense. So powers of L must be 0, so a plus b must be 0. And the time exponents 1 must be minus 2b. From which we conclude that b is minus a half and a is a half. Which means that, coming back to here, that t has the form of h over g to the square root. But to be careful not going too far in our conclusion. So that's in terms of units, dimensionally. So the way to write that is that t is some dimensionless quantity alpha times the square root of h over g. So the units of alpha are 1. And of course, I'm not actually solving anything, so it would be too much to expect that I work out the alpha just from doing this analysis. But on the other hand, we've got the right answer, right? And T land was root 2h over g. And just by thinking about the way the different units, the only ways they can combine in a sensible, in a meaningful way, is in that same relationship, a square root of h over g. Now this is quite useful. Even this, if I don't solve any differential equations, I have that. That already tells me quite a bit, because it tells me if I double the height, what happens to the landing time? Does it double as well? No, it goes like the square root. Okay, so even without that alpha, there's still sort of a useful kind of analysis. Okay? And more generally, take a physical system and play the same game. You have to be careful. You know, what are the physical variables involved? What are their units? And then pose a generic relationship of how those units combine, creates a linear algebra system for the exponents, and then you get a relation. Okay? So it's can be quite a powerful technique for it, of course, to be careful about getting the right ingredients to start with. But we won't do much with this, but I've put one problem like this in problem sheet 1. Okay, let's switch gears a little bit. I want to start talking about forces. So of course, in this story of Newton, forces are kind of key, right? Everything is driven by forces. What are forces? I mean, you can say forces are the things on the other side of m times r dot dot that cause motion. We're going to approach forces by thinking of properties and by examples, I think, as opposed to saying more generically. So one key point is that forces add. That's nice. And so that means that if I have a set of forces F1, F2, up to Fn, all act on the same particle, or object or mass, then when we write m times r dot dot equals F, the F that we use is just the sum of all of them. The total force is the sum of the FKs. And okay, in a way that's intuitive. This also can be quite useful because it means, as a corollary, if an object is not moving and it has multiple forces on it, actually if an object is not moving and it has a force acting on it, there must be another force balancing it. I used this argument on last time, say I'm standing here, I'm not accelerating, I know gravity's pulling me down, there must be another force acting on me, otherwise I would be accelerating, and that's the reaction force of the floor. Right? So the corollary is if a particle or if an object, if I can find a pen that lasts more than a word, let's try that one. If our particle is not accelerating, accelerating, squeeze that in, then the sum of the forces must be 0. simple consequence of Newton's second law. The r dot dot is 0. The right-hand side, the forces must be 0. This is sometimes nicely thought of in terms of what is called a force body diagram, which engineers love to draw. Forces are vectors, right? And if I have more than one force on an object, I can just draw an arrow for each vector, and the arrows must add up to the total acceleration, right? That's what a force body diagram looks like. So for example, this is kind of a nice intuitive one. If I have a block positioned on a slope, so here's a hill, and I have, okay, it's a box, but let's imagine it as a point mass. So not worry about surface area. Sitting there, and it's not sliding down the hill. If it's not sliding down the hill, then the forces must add up to 0. So let's think about what the forces are in that. So I have gravity. Let's put it here. I have gravity pulling it down. It's on a surface, and anytime we're on a surface, there's a reaction force which is normal to the surface. We're going to formalize that in a few minutes. It's the same as I was saying, there's a force on all of us right now up from the ground, whatever surface you're in contact with, which goes that way. And if I put that here, I'm just going to shift it. So I'll call that N. That's the normal reaction force. If I shift that over to here, the sum of those two things is not 0. So what am I missing? Yeah. Static friction. And you can just see I just need to complete the triangle. Right? So there's a force. And in fact, that tells me exactly what N must be and exactly what the friction force must be. So there's a force going this way, which we'll call F, I guess, maybe small f for friction. And that's a friction force, which is coming from the interaction with the molecules of the box and the molecules of the surface it's on. Okay. We'll say more about, for the most part, we'll keep things simple and consider frictionless surfaces, but we'll say a bit about friction in a bit later. Okay, let's talk about probably the most important force we can consider that will play a big role in the course is gravity. Gravity is kind of a funny thing, even for Newton. So there are two different forms that you see when you talk about gravity. And you can kind of roughly break it down into, if I'm near Earth's surface, or the surface of another celestial body, if I'm near Earth's surface, then I'm sure we've all seen this. Well, we've seen it a minute ago. Force of gravity is minus mg k, where k, that's Earth, which we're very close to, so it looks flat, and k is the z-axis pointing away, right? So minus mgk, and that g is the acceleration due to gravity, which is 9.8 meters per second squared. There's a sort of slightly subtle technicality here, which is worth at least mentioning. So we saw it over here. I have an m over here and I have an m over there. technically there are two different possible conceptual m's we might talk about. There's an m, which is this m, the m in the gravitational force. And for a moment, I want to call that mg. And that's called the that mg is called the gravitational mass. And then if I write down Newton's second law, I have mi times r dot dots equals minus mg g k. That mi is called the inertial mass. And at least in principle, you can think that these are kind of different things. The inertial mass is sort of a measure of how hard it is to change the inertia of an object, how hard it is to accelerate the object. Whereas the gravitational mass is a measure of how that mass interacts with the gravitational field, right, the gravitational force. And if you were just setting out creating this theory, you wouldn't necessarily be obviously clear that those are the same thing. Right? One is a measure of how hard it is to accelerate me, and the other is a measure of what gravity is doing to me. Okay? Since Newton wasn't really making this distinction, but in the years following Newton, people were making this distinction, and they empirically knew that these two masses were the same via measurements. And the simple measurement you do is you drop an object in a vacuum, and you see that it falls at exactly the same way, independent of its mass, right? Because the masses cancel each other out, and those masses only cancel each other out if they're the same, right? So lots of measurements show to a very high accuracy that those two things are the same. It wasn't actually until Einstein equivalence principle that it becomes a fundamental principle that these two things are the same. Okay? So we're not going to worry about this kind of detail, but just for completion of the story, and we don't really need to worry about even having these two symbols. For us, mi just is mg, and therefore an object falls under purely gravitational field independent of its mass, right? So r dot dot equals minus g k independent of mass. Okay, so that's sort of a side note. Okay, I think everyone's probably seen that formula and used that and probably done calculations like the one on the left. Maybe you've done calculations like this. Actually, if I'm in outer space, or if I'm thinking about the motion of planets or asteroids or things like that, I don't use that formula. I use a completely different one. So, in fact, there's the force on, well, I'll do it this way. We'll do it sort of via example, but it's a more general formula. The force on Earth due to the sun looks like this. I take minus the mass of the Earth times the mass of the sun times a constant that we'll call capital G divided by r squared. R is the distance between the two center of masses, and that's a vector pointing, I've run out of space. Let's see if I can squeeze in an ER there. So that's the sun, that's Earth. That has a length r, and it's in the direction ER. That's like polar coordinates. that g is a gravitational constant that is not specific to Earth. Sun is a sort of constant of the universe, if you want. This is a good place to understand Newton's third law. What does Newton's third law tell us in relation to what I've just written? Yeah.
The force on the sun by the earth due to the earth is the same.
Yeah. And here you can see the symmetry because I've got the mass of both of them multiplying each other. Right? Now what's a bit awkward or a bit hard to make sense of at first is these two formulas look quite different. This one depends on how far apart you are. This one's just constant. Actually, this is the proper formula. Well, or you could say, as far as Newtonian mechanics is concerned, this is the proper formula. And this is the same formula for the pen that I drop. Right? The pen falls under gravity. It's really, this is the most accurate thing I can write. The question is, where is that one coming from? We're going to explore that, I think, in detail a bit later in the course. Does anyone have a sense? What is the short answer is that the scales are so different. So if I drop the pen, it falls according to that. The r is the distance from the center of the Earth to the center of the pen. And in that little experiment, that r isn't changing at all, right? To a very good approximation, the r is just constant, and you get the 9.8 meters per second squared by taking mass of the Earth times g over the radius squared. Right? So this is a very useful approximation, but the further we get away, we need to think that that's the sort of truth. Okay, we will do a lot more with that equation later in the course, I think chapter 6. So let's use the top equation, the sort of simple version of gravity, and I want to claim that force, if that's the only force I have acting on an object, then I get parabolic motion. Well, I should say parabolic motion or linear motion. I don't think the result is surprising. You've seen this. If I throw something, it takes the shape of a parabola falling under gravity. But the claim here is totally generic. It says no matter what I do to the object, if that's the force acting on it, its motion, its trajectory will be in the shape of a parabola. I want to think, how can we try to show that? What we need is a completely generic set of initial conditions. So I need to consider a generic system, which means I have m r dot dots equals minus m g k, with r dot of 0 being a generic vector v, and r of 0 being a generic vector r0. And the claim is that if I solve that for arbitrary v and r0, then that path that the r traces out over time is in the shape of a parabola or a line. Right? Okay. So one thing I can do is I can just solve it. I'm going to do this quickly because I think we can all integrate that equation. So if I integrate that equation twice and apply those initial conditions, I get r of t is minus 1/2 gt squared k plus v t plus r0. And now I want to argue that as a space curve in R3 is a parabola. Okay. it's not surprising. I mean, you can kind of see it. It's a t squared. Squared tells me parabola, but I don't mean in time. I mean in the shape it makes as a curve in space is a parabola. So my trick I'm going to use is I've used generic v and r0, and now I'm going to do some without loss of generalities to make them not generic. That's our little trick. So without loss of generality, what can I do? When we're doing these without loss of generalities, the idea is that I have a coordinate system through which I measure r and v and r0. I can always translate and rotate that coordinate system. And as long as my force, for instance, doesn't depend on spatial position, then I've not lost any generality. I'm just describing vectors from a different origin and orientation. Right? So one thing I could do, for instance, is let's just put the origin at r0. So let r0 be 0. Now I've fixed the location of my origin. I still have one thing I can do. I can rotate the origin. So let's rotate the origin so that v is in a plane. So for instance, the ik plane. So I still have an arbitrary magnitude of v. And I'm going to write it as a vector, a unit vector in the ik plane that has some angle alpha, cosine alpha I plus sine alpha k. Notice that when I say rotate, I have to be a little bit careful about rotate my origin. I can't rotate the k because gravity is in the minus k, and I can't rotate that away, okay? So what I'm really doing is I'm rotating about the k. So whatever my v was, I'm just going to rotate the I to be aligned with, the ik to be aligned with that v, okay? So now the j direction is out of this. I can really just deal in the sort of x and z components. So as coordinates, we have that equation gives x of t is just getting the vt, so that's v cosine alpha times t. And y of t is just 0, and z of t is minus a half gt squared plus v sine alpha t. And those expressions, the capital V and the alpha, are arbitrary. Right? Okay, so I need to think about, there are two cases, really. So one case is when alpha is pi over 2, or 3 pi over 2. And what happens there? The cosine drops out. X is 0. Now this is the experiment where I just dropped the object. Right? Yeah. Is that a question? No. So in that case, that's linear motion. Right? The z is only moving in the z-axis. So x identically 0 falls straight down. And the complement of that, I have an x variable, and I want to say something about the trajectory itself, the path of the trajectory, which means eliminate the t from those two equations, so I get a curve, an implicit curve in the xz plane. And that's straightforward enough, because I can just solve for t as x over v cosine alpha, which means that z is minus 1/2 g times that squared plus v sine alpha t, which is minus 1/2 g x squared over v squared cosine squared, and plus, when I do v sine alpha, I just get x times t. I get tangent, and the v cancels out. So plus x tan alpha, which is well defined because the cosine is not 0, and that is a parabola in the xz plane. Okay. Okay. We've introduced the idea before of normal reactions and friction. Let's say a little bit more about those. Oh. So normal reaction, by the very word itself, is a force when an object is on a surface, pushing against the surface. It doesn't have to be due to gravity, but for the most part, that's the kind of case we'll think about. When an object is pushing against a surface, the surface pushes back, or otherwise the surface has to move. Right? So if the surface isn't moving, then it must be pushing back. And the normal component of that is called the normal reaction. Okay? So it's always going to be pointing normal to the surface. And for instance, as the case of gravity, the object is sitting there in equilibrium, and it's got minus mg k down, then n must be the opposite of that mg. If the object is not accelerating, right? We'll do a lot with normal reaction forces anytime we have surfaces involved. So it's always, anytime you see there's a surface, you need to think, okay, there's going to be a normal reaction force, regardless of the properties of the surface. Okay? Simple fact that this thing's on this pushing down, the thing must be pushing back in the normal direction. The other one, which is a little bit trickier, is the friction force. And friction is kind of a tricky topic on its own. The scenario that we'll at least talk a little bit about is the simplest version, which is called dry friction. Sometimes static friction. And this is the friction force that's there in the case where there's no motion. Okay? So go back to our block diagram, block on a slope. I said I have a normal force N, the friction force, just also useful, just think about the direction, right? What is the friction force doing? It's keeping the thing from sliding down the hill. It's pointing up the hill. Okay? So that's That's our F. And the statement is that the object doesn't slide so long as F is less than or equal to a constant called mu times n. That mu is called a friction coefficient. What does it mean? So that's a measure of kind of how sticky the surface is. So if the surface is ice, for instance, mu gets very, very small. And what is this doing? It actually becomes a geometric relation on how steep the slope can be before the thing slides. You can see that, right? If I compare that picture to this picture, if I make it very steep, and I have the same gravity pulling me down, the relation between n and F changes so that F grows compared to n as I increase the steepness of the slope. So the mu there dictating, really there's an angle, I think it's like a tangent of mu or something like that, that'll tell you the critical angle, and if I'm steeper than that angle, then F is greater than mu n, and then it slides. And once it starts sliding, then friction becomes more complicated, and we won't do anything with that. But I think there's at least a bit of intuition there. So it's, yeah. The diagram shows us that as I increase the steepness, the F grows compared to the n, and that's my condition for not slipping. Okay. Let's talk about a different force. Force of drag. So drag is a force I think everyone has an intuitive sense of what drag is, right? It's a force that resists motion. If it's resisting motion, then as a vector, it must be pointing in the opposite direction of whichever way the object is moving. Right? Let's say it points in the opposite direction of motion. So what does that mean if I have, let's say that's the trajectory of my object. This is r of t. Then at any given moment in the motion itself points in the direction r dot. And so r dot, the tangent, is that way, and drag must be pointing that way. Okay. It's a more complicated force, right? Because the direction of the force depends on the motion of the object. So fundamentally, drag is trickier to deal with mathematically, and most of the problems we'll just neglect drag because it's kind of a drag and it makes our nice energy conservations fall apart and things like that. But it's worth at least observing it. And there are two kind of main forms you might think about. So the easiest one is called linear drag. And this is, well, when the form of the force is linear function of r dot. So that's like saying F, the drag force, is minus B so linear in the velocity. So the velocity is the magnitude of r dot. And pointing in the direction, I need a unit vector pointing that way, which I've already put the minus there. So now I need an r dot over r dot. That might not look like a linear expression, but it is, right? Because r dot over r dot is a unit vector. And that says that the force is a linear function of the velocity of the object r dot, magnitude of r dot. And actually this works out nicely because the magnitudes drop out and we just get minus b r dot. And that b is a constant that depends on the setup in the experiment and whatever it is. But sort of a simple example where that law is quite accurate is if you have an object falling through something very viscous fluid. So for instance, take a little bead and drop it through syrup, and the drag force comes out very closely linear, called Stokes flow. So if I have a sphere in a viscous fluid, example, syrup. Example, not. The drag you experience if you cycled here this morning, that's not a very good model for that. The drag that an airplane experiences flying, that's not a good model for that. For things like that, most objects moving through air, you need quadratic drag. And, well, it's going to construct in a similar way. The force F is some constant I'm going to call CD for now, magnitude of r dot squared. So the force is quadratic in the velocity, and again, it's pointing, I need the unit vector pointing the other direction, which is my r dot over magnitude of r dot. So that, of course, becomes minus CD r dot r dot. That CD is the drag coefficient, and if it's an object moving through air, CD has some form like this, 1/2 we'll call it d rho a squared, sorry, a not squared, 1/2 d rho a, I think it's that. So there, rho is the density of the air. A is the cross-sectional area opposing through which is the direction of motion. So this is an area. This is a density. And that's a dimensionless constant that depends on the shape. So for instance, you might consider an object with a big surface area moving this way. Why do I get drag? Because the air has to get out of the way, right? And the wider that is, the more area that there is, the more air has to get out of the way. And so you get a higher drag. So compare that versus that. And as I said, it's not really a block. It needs to be a three-dimensional object. That D is doing something with how the air flows past it. So if I have something like a nice sort of aerodynamic looking shape like that, that might have the same area as that one, but the air can flow around that one better. Okay. Okay. Mathematically, that's much harder, right? I've got a magnitude of r dot. R dot is x dot, y dot, z dot. So I've got a square root of x dot squared, etc. Leaving in my force equation, that's very messy, right? Quadratic drag is accurate, but very hard to deal with. Nevertheless, in some cases, we can still make progress. So let's suppose that a particle, well, I'm going to do two things. Particle falls with drag force F, let's call it F equals B F1 that, or and I asked the question, what is the terminal velocity? So this is a feature if I have drag, then gravity is accelerating me that way, but I have forces pushing back that way, and at some point they balance each other. In this first case, where it's linear drag, and this is one-dimensional motion, so the equations aren't that bad. It's just like a z dot. In this first case, I could just solve m z dot dot equals minus, so in case 1, equals minus b z dot minus mg. Sorry, to be careful about my, all right, let's do it this way. So z is up. So z is pointing up, z dot dot, mass times acceleration, has a minus mg, gravity going down, and a z dot, I need that one pointing up because I'm moving down, I'm falling, drag force opposes, so it's pointing that way. I could solve that equation for z, integrate, and you're going to get like an exponential solution plus something else, and then you look at the velocity, and you take the limit as t goes to infinity, and the exponential bit drops out, and whatever you're left with, the velocity goes to a constant. You can get it that way. But an easier way is to just say, well, what happens at terminal velocity? By definition, terminal velocity is the velocity at which you don't increase beyond. So by definition, terminal velocity has z dot dot equals 0, and I can just solve this now. Z dot dot equals 0. That is the velocity. So I would just get b times v terminal equals mg. So my terminal velocity is mg over b. And in the case of F2, with the quadratic drag, I can't even, that's much harder to even integrate. So I can't, I mean, it is actually possible, but it's harder to just integrate. Nevertheless, this calculation works similarly. So if I take z dot dot equals 0, and I balance, so that's like a minus cd, and that's just a z dot squared in 1d. So I just get mg minus m g plus c d z dot squared, and I get therefore that the terminal velocity v term is square root of mg over cd. And you can see that it has quite a strong impact. One goes with the square root of the mass, the other one goes with the mass. Okay. One last thing, and then we'll stop for the day. So I think these kinds of systems, sometimes they're very intuitive, right? Because I think the fun bit about mechanics is the bits that are not intuitive, at least not initially intuitive. And so throughout the term, I want to give you some thought exercises. They don't count for anything. You don't have to do anything with them. You can discuss them at some point later if you want. But just exercises to get you to think about some of the concepts we were playing with. And so the first one I'll give you, it's very silly, but it's the following. So you know, if I'm in a vacuum and I have a rock in this hand and a leaf in this hand and I drop them, they fall at exactly the same rate. Yeah? We also know that if I'm in air and I drop the rock and the leaf, what happens? They don't fall at the same rate anymore because there's drag. Which one falls faster? The rock falls faster. Why does it fall faster? Okay, it's got a higher mass and it's got a lower drag coefficient because the leaf has this big surface area. And there's two things there: higher mass, lower surface area. Okay, so here's the question I leave you with. What would fall faster in air? A rock-shaped leaf or a leaf-shaped rock? And we'll stop there.